All right, factoring, breaking a number or expression into product of its factors, also known as division. Okay, so factoring is another word for division. Just keep that in mind. When we're breaking something up into factors, we're finding things that multiply together to give you that item. So for instance, one of the things that we look for is what's called a greatest common factor. Sometimes it's a number, sometimes it's a variable, sometimes it's a combination, what we call a product of numbers and variables. That would mean you would have something like a number and a variable multiplied together. Like for instance, in the first one, I noticed that both of them have not only a 5, but they also have an x in common. All right, now, most people do not want to have an x in common. Okay, typically means it wasn't a good relationship. Yes, that's just a joke, folks. But it is a true joke. All right, so I'm going to zoom in on this for a second because I needed to see something. What I'm going to decide to put inside here and here are the remainders, what's left after I take the 5x out. Now, remember I said I was dividing, so each one of these is getting divided by 5x. Whatever that is will go here, whatever that is will go here. Of course, plus will be in the middle because we started with a plus. So in the first one, it looks like we have 3 and x left. Keep in mind that if you would multiply these together, again, you would go back to the beginning at 15x squared. Not that we want to do that, but that's what would happen. In the next one, the x's would be eliminated and 25 over 5 is just plain old 5. So, that is my final answer to this question. I took the 5x out, and that left me with 3x plus 5 trapped inside. What's in the blue box is equivalent. It is equivalent to what I started with. It's just written in a different form. So if I go to the next one and look at it, they each share, let's write that down a little bit farther. They each share a 4 and an x. Remember that what you're doing is you're dividing each one of these by 4x. Of course, there will be a minus in between this time. And the first one would be 2x. And the last one would be a 1. So that's your final answer on part B. In the next one, only 4 can come out. So only 4 can come out. There's no x involved in both of them because you can't get an x out of 12. There's no x there. So we can pull a 4 out, giving me 2x and a minus 3. There's my final answer on that one. All I'm looking for are greatest common factors. Looks like we have a 3 in common to each of those, so the 3 comes on the outside, and I'm left with 2x plus 1 trapped on the inside. Go down to letter E. Now, on letter E, I'm going to suggest to you that we pull out a negative 7. A negative 7. So I'm going to divide each one of these by a negative number this time. There's a real reason why I'm doing that, because I want the thing left on the inside right here with the x to be a positive. Now that will become more apparent later why that is more of a common practice. And then of course I have minus 2. But in that case, I took a negative greatest common factor out. We can always take a negative out, but sometimes it has its advantages, and that's the real reason, is exactly what you're seeing right there. On the next one, I can divide each one of these by 9, so 9 comes on the outside, and that's x minus 3. On the next one, I've got 3 and x that can come out of each of those. So that would be, 3x is on the outside. And that leaves me with 1x minus 16 on the inside. Oh, got one more. looks like they each have a 2 and an x. And so the 2x goes on the outside. And that would leave me with 10x plus 1 on the inside. 10x plus 1. You're just simplifying the two fractions to figure out what goes in the parentheses. All right. Factoring a quadratic trinomial where a equals 1. That's next on our list. That probably goes with the next slide, to be honest. Yeah. Yep, that's the title of the next slide. It accidentally got put on the last slide. Oh well. So, when a is equal to 1, that's the big deal here. So, we know we have ax squared plus bx plus c. We want to break this into two parentheses. Now, the only way to get x squared, the very first one, is if this one's an x and this one's an x. Okay? What we're basically doing is reverse engineering FOIL. If you remember FOIL, firsts, outsides, insides, and lasts. You might have seen in your Algebra 2 class, you know, the firsts, that's found by taking this one times this one. Then there's the outsides. Then there's the insides, and then there's the lasts. We would basically, there's lots of distributing going on and like terms being added together. But in order to come up with that x squared at the beginning, you have to multiply this one and this one together. So that can only happen with x and x. The last one can be found by multiplying. I need two things that multiply together to give me 24. Okay? Now, you'll notice that right here it says multiply a and c together. That's pretty boring right now because you've got a 1 and a 24. Well, 1 times 24 is 24. In the future, that's not going to be a 1, and that will make a difference. But it says right here that they have to add up to the b value, which is 10. So let's think about our factors of 24. I want you to notice the way I'm writing them. I've got 1 times 24. I've got 2 times 12. I've got 3 and 8. And lastly, 4 and 6. Now, you're probably wondering, why in the world did he write it in a V-shaped pattern? Because as the factors get closer and closer and closer together, what I want you to realize is that you have run out of options. There are no more options. 5 does not go into 24. Now, which one of those combinations adds up to 10? Well, of course, it's this one down here. So we're going to have a plus 4 and a plus 6. Those two things multiply to 24, but when you do the outsides and the insides, you add up to 10x. So this is the correct factored form for example 1a. Right there it is. X plus 4, x plus 6. Now, some of you might say, well, Mr. Stailey, what if I wrote x plus 6 and x plus 4? Is that okay to do that? Of course it is. Because all you've done is the commutative, if I can spell this right, commutative property of multiplication. That's one of those properties that we talk to you about every single year, usually. And at the very beginning, you know, can you 2 times 3, is it the same as 3 times 2? Of course it is. Okay, so once again, here we have an a value of 1 and a c value of 6. 1 times 6, which is 6. And they have to add up to 5. So let's look at our factors. 1 and 6, 2 and 3. Now, 6 with the 5 in the middle is a tricky combo. Now, I know what you're saying. You're saying, Mr. Stailey, it's not that tricky. I mean, for crying out loud. Literally, it's 2 and 3 right there. Well, there is coming a factoring where this sign is going to be a negative. And when that's a negative, you're not going to be using 2 and 3 because the only way to get a product of positive 6 is if both are negative or both are positive. So I get why you would use 2 and 3 this time. But if that's a negative on that 6, then we're going to need 1 plus and 1 minus. And in that case, we will be switching to the 1 and 6 because that's the only way to come up with like a positive 5 or a negative 5. I know, you're probably listening to me going, Mr. Stailey, this doesn't make any sense. Well, maybe I should just write it out right now because it is coming. X squared plus 5x minus 6. You'll have an x here and you'll have an x here. But the only way to get a negative 6 is if one's plus and one's minus. In this particular case, I have to add up to positive 5, so it would be a positive 6 and a negative 1. You're not using 2 and 3 because that would not add up to positive 5. So, I do know what I'm talking about. I have seen kids make mistakes on that one. So, we will look for that. When it comes up, I'm sure it will. Example 2, factoring. All right, continuing to factor. These are just more additional, ideas. So now that we kind of got the idea, we're going to do x and x. We need to multiply to 33. Let's see here. I didn't leave myself a whole lot of room here. So let's do it down below. 1 and 33. Let's see. 3 goes in 11 times, and that's about it. Those are my only options. We do want to add up to a negative number, so these are both going to be negative since they have to multiply to a positive. And let's see here. The only combo that works would be 3 and 11. So there's my final answer there. Oh, by the way, every single time I do these questions, my first thought should be, is there a greatest common factor? And if there's no greatest common factor, I just go ahead and start doing the stuff that I'm doing. If there's a greatest common factor, we got to deal with it first. No GCF here. Let's see here. Because that's a plus, both signs have to be the same. And this one tells me that they both are minuses. So now I think about my factors of 12, 1 and 12, 2 and 6, 3 and 4. Which combo adds up to 7, or in this case, negative 7, so it'd be a 3 and a 4. And so there's your factored form for that one. When we get to the next one here, we got an x, we got an x. Okay, so they both have to have the same sign, and they both need to be negative. Okay, now we need factors of 81. 1 and 81, 3 and 27, 9 and 9. Okay, they need to add up to 18. I think it's going to be this one right here, minus 9, minus 9. Now, this is technically correct and would be accepted on any test. But I need you to also understand that whenever you multiply something times itself, you can say this. X minus 9 quantity squared. That is exactly the same. All right, next slide. Example 3, factoring. More factoring. Still using a values of 1, but now, we're going to be dealing with a negative number. So if you are coming up with a negative number here, that means that when they multiply together, they have to be negative. The only way that can happen is if you have 1 plus and 1 minus. Okay? So lots of times you'll see me write M there for multiply and in the middle A for add. Now truthfully, that only applies if the lowercase a value is a 1. So, you got to be careful when I write that stuff down. Factors of 28, we got 1 and 28. We got 2 and 14. 3 does not go into 28. 4 goes into 28 7 times. Now, it's going to be this choice right here, as long as you make this a positive 7 and a negative 4. And you might ask yourself, does it matter which one I put where? And the answer is definitely yes, because yours have to add up to positive 3, and if you switch those signs, it would add up to negative 3. And that would not technically be correct at all. So, on the next one, you can see what they have to multiply to, and they add up to, negative 1. Negative 1. So let's see here. We've got x and x. One's a plus, one's a minus, because they got to give a negative 30. And so let's look at my factors of 30. 1 and 30, 2 and 15, 3 goes in 10 times, 5 goes in 6 times, and that's it. Okay, so which one would give you the combo that adds up to negative 1, right? You got a negative 1 right there in the middle. That would have to be a negative 6 and a positive 5. That's the combo that's going to get us there. Part C, or example C here. So I got an x there and an x there. We got a plus and we got a minus. Factors of 10, we got 1 and 10, or 2 and 5. Not a whole lot of options. We're trying to get it to add up to 3, so I think it's going to be this one right here, positive 5, negative 2. And that is true. Positive 5 and a negative 2 would add up to positive 3. Okay, so I noticed there's a greatest common factor here before we continue. So the first thing I want to do is pull out the greatest common factor. So I went through and I divided each one of these things by 3, just like we did at the very beginning. But then I noticed that I could keep going. I could continue factoring. This is why they use the term completely. Whenever they say that, there might be more than one step. Might be. Not saying there is, but there is in this case. So we got an x and an x. Because that's a plus, I know they'll both be the same, and they'll both be negative. Both be negative. But you only got one option here, 1 and 3. And since they're both negative, it's kind of hard to screw that up. Now, is it okay if I had 3 times x minus 3 times x minus 1? Of course it is. That's the same exact thing. No big deal. I mean, you could put this 3 that I have over on the left side, you could pull it all the way at the end. I don't care, but you're never going to see that happen. Well, once again, here we're going to pull out a negative 2. This is where I'm going to go through and divide everything by the greatest I'm using the negative because I want to get rid of it and pull it out. Okay, so that's going to leave me like this, and a minus 21. Okay, so now we look to factor it further. I do notice that I've got a negative right here, so that's going to give me a positive and a negative. Of course, that's going to be x, and that's going to be x. Now, 21, we got factors of 21, 1 and 21, 3 and 7. Obviously, it's going to be 3 and 7, with the 3 being negative and the 7 being positive, so that they can add up to positive 4x. Now, I hope this has been a nice trip down memory lane for you, as is the next thing. Every single one of these is a perfect square. 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, and so on. These are called perfect squares. Now, if you are factoring a difference of perfect squares, you got to think about this right here. I'll do it over here on the right side so that it's easier. The middle term is missing. We have said before in a previous lesson that if the middle term is missing, that must mean that the b value is 0. We know that it has to multiply to this one, but add up to this one. Well, the only way two numbers add to 0 as if one is the opposite of the other one. Right? So as you're setting this up, x and x, one's a positive, one's a negative, what numbers are there that multiply together? Let's do this and this. No, that ain't it. Come on, erase. There we go. What numbers multiply together to give you 36, but add up to 0? Well, of course, they would have to both be 6. Now, what is the moral of the story? If you took the square root of this one, and you took the square root of this one, and you made one a minus and one a plus, you have the answer. You have it factored. That's what I should have had right there on that line. So if you take the square root of this one and the square root of this one, that would be 1a, 1a, 1b, 1b, 1's a plus, 1's a minus. I am finished with the factoring. Differences of perfect squares are supposed to be easy. So, not a bad thing at all. Very, very simple, very, very straightforward. We'll see some more examples here in a second. All right, so square root, right? That's just going to be x plus 5, x minus 5. Square root, x plus 7, x minus 7. Now, before you start slapping square roots everywhere, don't forget to look for greatest common factors like this. Right? You can divide each one of those by 3 and get x squared minus 16. Oh, look, a difference of perfect squares. So this is like step 1, step 2 kind of stuff. And you can look here and go, oh, I can do square root, right? So 3, and then you've got x minus 4 and x plus 4. Now, is there anything that goes into 100x squared and 9? No, there's not. So, and they both happen to be perfect squares. So I'm going to take the square root of each, and I'm going to go 10x, 10x, 3, and 3, and 1's a plus, and 1's a minus. Straightforward, folks. Square root, 1's a plus, 1's a minus. Any GCFs on the next one? Nope. So square root. So 8x, 11, 1's a plus, 1's a minus. Done. It really is pretty nice. It's not really like super hard to do that. Just make sure you look for the GCF, because that would definitely, if you see two terms that are being subtracted like that and you suspect that there's a difference of perfect squares, look for a greatest common factor first, and then you might go, oh, well, there it is. All right, let's see if there's anything else. And nope, that's it for the video for this particular lesson.